All right, so in this video, we're going to take a look at some intermolecular forces and compare the relative strengths of those intermolecular forces, and then put that within the context of all the different types of bonds that we learned about in Unit 2. So when we're looking at intermolecular forces, there's four of them we think about. There's dispersion, dipole-dipole, hydrogen bonding, and then ion dipole. And then ion dipole is a little bit of a misnomer if we're calling it an intermolecular force, because we only actually experience this when we have solutions, which would be in the context of a mixture of something that is ionic and something that is polar. So these three types can occur in like a pure substance by itself, or in a mixture as well. But we typically think of dispersion force as being weakest, then dipole-dipole, and then hydrogen bonding. It's important though to notice that dispersion forces actually vary with size. So this comparison of saying this is the weakest and this is the strongest, that only works when you are comparing molecules of similar size. So I'm just going to put a little note over here to the side. So this increasing strength is only true when you're comparing things of similar sizes. And that's because molecules with larger electron clouds are what we call more polarizable, which means the polarizability is a description of what's going on in here in an electron cloud that causes these dispersion attractions. So you have this electron cloud, the electrons can move around and they create these temporary moments of asymmetry where we get this temporary dipole. And then we've got this temporary dipole, there's a temporary positive and negative, it's going to attract to a nearby molecule doing the same thing, and that is the source of these dispersion forces. And when we're thinking about the size of a molecule, we want to think about the size of its electron cloud. So think about like periodic trends when you're thinking about comparing sizes. So yeah, it's all about the size of the electron cloud. And when they have a larger electron cloud, they're more polarizable. That will lead to stronger dispersion forces, to the point where a large nonpolar molecule may even have stronger IMFs than a small polar molecule. And this is something that we observe in the surface tension lab. So what I did is I have our data from the surface tension in order from lowest surface tension to highest surface tension. Water's got the highest surface tension, it's got hydrogen bonding. But notice that decane, even though it's nonpolar and only experiences dispersion forces, it actually has a higher surface tension than methanol, which is capable of hydrogen bonding. That's because decane is very large. So it's got a large electron cloud. So we'd say it is very, polarizable, and it's going to have relatively strong dispersion forces. And sometimes people refer to these as London dispersion forces. You might see the shorthand LDF, stands for London dispersion forces. And here's another side-by-side comparison of this. So we've got iodine, which is definitely a nonpolar molecule. We've just got two atoms that are exactly the same. So this is nonpolar, versus water. And in iodine, it's nonpolar. It experiences dispersion forces only. Water is polar. It can hydrogen bond. But if you look at the data, like the boiling point in the state of matter, iodine's got a higher boiling point than water. And iodine's a solid at room temperature, whereas water is a liquid at room temperature. And this data right here, the boiling point comparison, tells us that iodine has stronger IMFs than water does. And that's because iodine is larger. It's got a larger electron cloud. Whoops, sorry about that. So it's got a larger electron cloud, so it has very strong dispersion forces. And I tried to show a picture of how iodine is larger, because it might not be obvious from this comparing these molecules that iodine is actually larger than water. It's because if you look at a periodic table, iodine is really low on the bottom right-hand corner, so each iodine atom is pretty big. And so an I2 molecule is actually bigger than a water molecule. I don't know if you can kind of see this a little bit here in this diagram. So there you go. Another application of our periodic trends. We're thinking about the size of atoms. There's some more practice with intermolecular forces on page 5. We'll come back to that later. So now let's put this in the context of bond types. So if you want to think back to Unit 2, and within the context of ionic bonds, covalent bonds, metallic bonds, We can remember what's happening to the electrons in these different types of bonds. I like this visual. You might remember it from regular chemistry. The shaded areas represent the electrons. And so you can see that maybe they're shared, or maybe they're transferred, or maybe it's all one big network of sharing. This is a good visual comparing what's happening here. And here's an overview of what's happening when your atoms bond. So if you've got all metals, it's metallic bonding. You can have a pure metal or an alloy. If you have metal and non-metal, form an ionic bond. And if it's all non-metals, you can either make molecular covalent or network covalent. And let's think about the forces that hold all these different types of things together. So if you have, a beaker full of water, right, which is a molecular covalent substance, what forces is holding together those water molecules? Well, in the case of molecular covalent, the force holding your sample together is these weak intermolecular forces. So the properties such as melting point, boiling point, state of matter, surface tension, all those things are determined by the strength of these intermolecular forces. If you're looking at an ionic substance, there's no such thing as an IMF when you're talking about ionic substances, because they're not molecules, okay? They're ions, they're something totally different. So if you remember when we talked about ionic substances in Unit 2, we talked about the lattice energy, and we looked at Coulomb's law and thought about the Coulombic attraction between those ions there. So when you're looking at an ionic substance, you want to think about the ion charge and the ion radius. So as a charge increases, the lattice energy, the attractive force increases. As the radius increases, that attraction is going to decrease. If we're looking at metallic substances, we've got this electron C model, and we can get into some more detail about what's going on with metals. You can notice that some metals have relatively low melting points, some have relatively high melting points. Explaining what exactly is going on here is beyond the scope of this class, so you won't be asked to kind of compare the bond strengths of metallic substances. Don't worry about it. I just want to throw it in here as a reminder that this bond type does exist, even though we tend to ignore it a lot. And then network covalent. So our network covalent substances tend to have very high melting points because in order, the forces that are holding this together it's all bonds. Like every atom is like covalently bonded to atoms surrounding it. So in order to melt a network covalent substance, you actually have to break covalent bonds, which takes a lot of energy. And so here's a comparison. When I say the intermolecular forces are weak, I wanted to give you some quantitative info to back that up. So if you look here, there's a range, of course, but this is kind of the relative energies it would take to break apart these types of attractions. Notice that the intermolecular forces are much lower than the covalent bonds or ionic bonds. So it'd be much easier to break an intermolecular force than a bond. So this is really a key takeaway here. Other thing that's important to notice is that ionic bonds and covalent bonds are relatively similar in strength. There's variation, depends on what you're talking about, single bond, a triple bond, double bond, depends on which ions you're attracting. But ionic bonds and covalent bonds, there's a lot of overlap in the energy here, but what they have in common is they're both much stronger than intermolecular forces. And again, here's a kind of a side-by-side. If you're considering properties such as melting point, boiling point, surface tension, when you're looking at a molecular substance, you want to consider the strength of those intermolecular forces. That's what's holding the sample together. If you're looking at something that's network covalent, it's those covalent bonds that's holding the sample together. So, and those take a lot more energy to break, so they're going to have a much higher melting point. Same thing with the ionic bonds. What's holding the sample together here is those attraction between ions. So that basically ionic bond. So in order to melt it, you have to break those apart, which takes a lot of energy. So that has to do with why ionic substances have higher melting points than molecular covalent substances, is because in order to melt an ionic compound, you actually have to overcome those attractions between ions. So you actually have to break the ionic bond here. If you compare this to molecular covalent, when you're melting a molecular covalent substance, no bonds are broken. All you're doing is you're moving those molecules apart from each other. And these IMFs are much weaker than the ionic bonds over here.